In this session, we look at the class of numerical integration methods based on undetermined coefficients. Basically here, we start by the Gauss-Legendre methods. Previously, we looked at the Gauss-Legendre methods and we saw that the Gauss-Legendre method are like a one-point method. We have the one-point method, we have the two-point method, three-point method, and so on. The one-point method can be expressed as the integral from -1 to 1 f of x dx is equals to 2 times f of 0. So that in this case, we only need to evaluate the value of the function at 0 and multiply the results by 2, and we get the value of the integral. The two-point method can be expressed as integral from -1 to 1 f of x dx is equals to the value of the function evaluated at -1 over root 3 plus f of 1 over the square root of 3. So we just need to evaluate the value of the function at -1 over root 3 and the value at +1 over root 3, add the two results. So we also saw that if the limits of integration for the function given is not -1 to 1, if you're given any interval a to b, we can transform this to -1, 1 using the transformation x is equals to b minus a all over 2 times t plus b plus a all over 2. So that if you're given any interval which is different from -1 to 1, the first step will be to transform that interval to -1, 1, then we apply the method. We can do an example on the use of the Gauss-Legendre methods. We can do a one-point method. You are given a problem. You are told to use the Gauss-Legendre one-point method to evaluate the integral I, which is given as the integral from 1 to 2, 2x divided by 1 plus x raised to power 4. We first note that the limits of integration differ from what we intend to use, because the method would be the integral from -1 to 1 f of x dx is equals to 2 times f of 0. This is the Gauss-Legendre one-point method. Because in order to apply this method, the lower limit of integration must be -1 and the upper limit must be +1. We start by doing the transformation of the limit. So we need to transform the interval of integration from 1 to 2 to -1, 1 by using the transformation that we have talked about here. X is expressed as b minus a over 2 times t plus b plus a over 2. B here, or rather a, is equals to -1 and b is +1. So we write x is equals to b minus a over 2 times t plus b plus a over 2. So a is 1, so that in this case, and b is 2. So in this case, we get 2 minus 1 all over 2 times t, then plus 2 plus 1 all over 2. See that 2 minus 1 here is 1. So this becomes a half t, and 2 plus 1 is 3. So that we get 3 over 2 in the second term. So we get a half t plus 3 all over 2. We can even factor out a half, and we get a half into t plus 3 as we have here. Then we now differentiate this. If we differentiate this function with, if we differentiate x with respect to t, we get a half. And so dx can be expressed as a half times dt. So our integral, which was integral from 1 to 2 into 2x divided by 1 plus x raised to power 4 dx, will now be expressed as integral from minus 1 to 1. The limits of integration will have been transformed to 1 to 1, but also x will be transformed now, will be expressed as a function of t, as we have here, a half into t plus 3. So we shall write 1 over 2 into t plus 3 as our x. Same in the denominator, 1 plus 1 over 2 into t plus 3. That is our x. So we shall raise this to the power of 4. And see, we also have dt, dx in our integral here, and dx is expressed as this, a half dt. So we shall write here a half times dt. So we simplify this, or we don't necessarily need to simplify. We can just write this one. We see the numerator. We can write it as 2 times a half will give us 1. But we have this half here, which we can write as a half. Then the integral from minus 1 to 1. The numerator becomes t plus 3. And the denominator is 1 plus a half into t plus 3 raised to the power of 4. And this one now we need to integrate with respect to t. So when working out this, we can choose to simplify this first, or we can just apply the formula, because in our case, the formula is the integral from 1 to 1 f of t. We can now write it in terms of t is equals to 2 times f of 0. So we only need to evaluate the integrand at 0. So we only need to evaluate the expression t plus 3 divided by 1 plus a half into t plus 3 raised to the power of 4. We just need to evaluate this when t is equals to 0, so that we get 0 plus 3 divided by 1 plus a half into 0 plus 3 raised to the power of 4. And we see now this one is very easy to work out. The numerator is 3. The denominator will be 1 plus 3 all over 2 raised to the power of 4, which we can work out. Once we work out this quantity, then we shall multiply by 2. But notice that we had a coefficient. We had a coefficient here, which is a half. A half here. So a half times 2 will give us 1. So we just substitute 2 times 1. 2 times a half is 1. So whatever we get here, we just multiply by 1, which means that this will be our final solution. So this will be 3 divided by 1 plus 81 all over 16, which we can work out this. So 1 is the same as 16 over 16. So we get 3 divided by 16 plus 81 all over 16. 16 plus 81 is 97. And when we are dividing a number by a fraction, then we take the reciprocal of the denominator, so that this one becomes 3 times 16 all over 97, which will give us 48 all over 97, which is our solution. So see that we can work out directly here without simplifying this. We don't necessarily need to simplify because we are only looking for the value of the function in here when t is 0. When t is 0 according to our formula. So we just substitute, then simplify after substituting. Alternatively, we can simplify as we have done here. We multiply out here, we multiply by a half, we simplify to get this expression. Then we substitute t is equals to 0, and then we shall multiply by 2 as per the formula. We end up with the same result. So we say that we have 8 times 0 plus 3. Then the denominator is 16 plus 0 plus 3 raised to power 4. And we get the numerator here is 24. The denominator is 97. Then we multiply by 2. Get 48 over 97. We can have another example. We use the Gauss algebra 2-point method. You are given the integral here. Again, the limits are from 0 to 1. The intention, as per the formula, the limits of integration should be from minus 1, to positive 1. So again, we use the transformation here. The value of a is 0, the value of b is 1, so that this one becomes 1 minus 0 all over 2 times t plus 1 plus 0 all over 2, and this is a half into t plus 1. So again, when we differentiate, we get a half, so dx becomes a half dt, and now we substitute again. So where we have x, we are now going to put a half into t plus 1. So we have x here, we have x here, so we substitute. And we can simplify this, which will give us t plus 1 in the numerator and t plus 3 in the denominator. According to the 2-point formula, we have the integral from minus 1 to 1 of f of t dt is equals to f of negative 1 over root 3 plus f of 1 all over the square root of 3. So in this case, we need to evaluate this function. When working out this integral, the integral I will become, notice that we have a coefficient which is half. So this one will become a half times f of negative 1 over root 3 plus f of 1 all over the square root of 3. Notice the coefficient I have, because the integral here will be expressed as per this formula. So the expression inside the bracket, but we have the coefficient, which is a half. So when we do that, we simply need to evaluate the value of t plus 1 divided by t plus 3 at those 2 points, then add the results. So we substitute. We have a half into t plus 1 over t plus 3 evaluated at t is minus 1 over root 3. And the same quantity evaluated at t is 1 over root 3. So when we work out, the result is 4 all over 13. So we can apply this method to any other interval. But we can also develop our own methods similar to using the same method. We can develop our own method to solve a particular integral. Suppose, for example, we are faced with a problem of evaluating an integral such as, say you have 0 to 0.5 e raised to power x divided by 1 plus x. You see, this kind of an integral is not easy to work out using the ordinary methods of integration, the ordinary analytical methods. So suppose we want to develop our own two-point method. Suppose we wish to develop our own two-point method. So we can start by writing our integral from 0 to 0.5 of f of x dx is equals to a times f of some value plus b times f of some value here. We can pick the value, some values of x between 0 and 0.5. I'll pick a value like 0.1 here and 0.45. So provided that the nodes are between 0 and 0.5. So we only need now to find the values of a and b. We need to find the values of a and b. So in this case, we note that this method that we have written here has two unknowns. The unknowns are a and b. So it means that this method can be made exact for a polynomial of up to degree 1. That is, we can write f of x and take the values 1 or x. Then we see that if we set f of x is 1, that is, when f of x is equals to 1, then we get this one is a constant function. F of x is 1, so we substitute 1 here, we substitute 1 here, we substitute 1 here. And we get the integral from 0 to 0.5 of 1 dx is equals to a plus b. So if we integrate this side, the left-hand side, we get x increases from 0 to 0.5, and this is equals to a plus b, so that we get a plus b is equals to 0.5. This is one equation. I will call it equation 1. And then we can go back now. We have used f of x is 1. We now use f of x is equals to x. So if f of x is equals to x, then the function here is equals to x. The value of at 0.1 will be 0.1. The value at 0.45 will be 0.45. So we get the integral from 0 to 0.5 of x. We integrate with respect to x is equals to a times 0.1 plus b times 0.45. So in this case, we get 0.1a plus 0.45b is equals to x squared over 2, and x increases from 0 to 0.5. So that we get 0.1a plus 0.45b is equals to 0.5 squared divided by 2, which will give us 0.1a plus 0.45b is equals to 0.125. So this is a second equation with two unknowns. I'll call it equation 2. So now I have two equations. Equation 1, which is up here, a plus b is equals to 0.5. And equation 2, let me write equation 1 again here, a plus b is equals to 0.5. This was my equation 1. And then I have equation 2, which is this one. So we are now faced with a problem of solving for a and b. These are two linear equations in two unknowns. So we can easily eliminate A here. See that if I want to eliminate A, I can multiply the second equation, equation 2 here, by 10. I can multiply equation 2 by 10. So I have, that is, if I multiply equation 2 by 10, I will have A plus 4.5 B is equals to 1.25. And then equation 2, we have A plus B is equals to 0.5. And now if I want to eliminate A, I'll get the difference between these two. And therefore, this side becomes 3.5B, which is equals to 0.75. And therefore, B will be 0.75 divided by 3.5. And this will give us 3 over 14. So once I have the value of B, I can get A, which is 0.5 minus B. This is 0.5 minus 3 over 14. This is a half minus 3 over 14. A half can be expressed as 7 over 14. So 7 minus 3 is 4 over 14, or even 2 over 7. So A is equals to 2 over 7, and B is 3 over 14. And now from the method that we had here up here, see the method we have, the integral from 0 to 0.5 f of x dx is equals to A times f of 0.1 plus B times 0 f of 0.45. So I'll replace A with 2 over 14, sorry, 2 over 7, and B with 3 over 14. So in this case, I'll have the method, the integral from 0 to 0.5 of f of x dx is equals to 2 over 7 times f of 0.1 plus 3 over 14 times f of 0.45. So now we can test this method to see if it works. I'll use a simple integral to test the method. We now test the method. Suppose now we write the integral from 0 to 0.5 of 2x plus 1. 2x, let me use 2x minus 1. X minus 1, integrate with respect to x. So our function here, f of x, is equals to 2x minus 1. So the value of this function when x is 0.1 will be 2 times 0.1 minus 1, which is 0.2 minus, or I can just leave it like that. Then the value at 0.45 will be 2 times 0.45 minus 1. Maybe I can evaluate this first. This is 2 times 0.45 will give us 0.9. So 0.9 minus 1, which will give us negative 0.1. And this is 0.2 minus 1, which is negative 0.8. So I'll now write the the integral from 0 to 0.5 of 2x minus 1 is equals to 2 times 2 over 7 times f of 0.1 plus 3 all over 14 times f of 0.45. We know these values. We have, so we substitute, we get 2 all over 7 times negative 0.8 plus 3 all over 14 times negative 0.1. If we work out this, the result is negative 0.25. You can confirm that the result is negative 0.25. We have dx here. Now, suppose we evaluate this integral directly, 0 to 0.5 of 2x minus 1. With respect to x, this becomes x squared minus x. And x increases from 0 to 0.5. So we get, this is 0.5 squared minus 0.5. And this will give us 0.25 minus 0.5, which is negative 0.25. And we say that the value we obtained here is the same as the value we obtained when using the method here, this other method, the method of undetermined coefficients that we have developed here. So it means that this method can give us the exact results. So in this case now, we can now apply this method to evaluate another integral. So if we have the integral that we had started with here, we wanted to evaluate this integral. We can now use the method that we have generated to work out this. So we can write the integral from 0 to 0.5 e raised to power x divided by 1 plus x dx is equals to 2 all over 7 times e raised to power 0.1 divided by 1 plus 0.1, then plus 3 all over 14. We have e raised to power 0.1 divided by 1 plus 0.45. So this one is now is to work out, and if we work out, we get 0.5188266 approximately. So you find that while the analytical methods may not be applicable to evaluate this integral here, but now using the two-point method that we have generated, we can easily obtain the solution. So notice that we picked the values. We picked the values, the points 0.1 and this one is 0.45, not 0.1. E raised to power 0.45. We picked the values because the formula, we have the integral from 0 to 0.5 f of x dx. We started by writing a f of 0.1 plus b f of 0.45. Now the nodes 0.1 and 0.45 are picked at random between 0 and 0.5. So they should be within the limits of integration. And then we can determine the values of a and b. Once we determine the values of a and b, then we write the method, which can be applied to evaluate any integral of this form, provided that the limits are from 0 to 0.5. So this method is applicable for the integrals of that form. And see, we can generate any other method. If we want to use a 2-point method, we can use a 2-point method. If we want a 3-point, we can still develop a 3-point method. We have an example here. Let me go to example number 4. You are given a problem like this one. You are, let me go to number 5. You are given a problem like this one. You are told to determine the values of a, b, and c such that this method, integral from 0 to 2 f of x dx, is equals to a times f of 0.5 plus b times f of 1 plus c times f of 1.5 is made exact for a polynomial of as high degree as possible, and then use it to evaluate the integral here. So the first thing is to determine the values of a, b, and c. We notice that the nodes 0.5, 1, and 1.5 are chosen in such a way that they are within the limits of integration. They are between 0 and 2. So we cannot pick the nodes outside this limit, this interval, 0 to 2. So, looking at the formula, we see that we have 3 unknowns. The unknowns here are a, b, and c. So, if the formula has 3 unknowns, then it means that it can be made exact for a polynomial of up to degree 2. That is, we can have 1x or x squared. So f of x can take the values 1, x, and x squared, so that we can generate 3 equations which will help us to determine the values of a, b, and c. So the method has 3 unknowns, and therefore it can be made exact for a polynomial of up to degree 2. And therefore f of x can take the values 1, x, or x squared. So then we consider the case when f of x is 1. And when f of x is 1, we substitute. Remember, the method was the integral from 0 to 2 f of x dx is equals to a times f of 0.5 plus b times f of 1 plus c times f of 0.5. This was the method. So when f of x is 1, we shall put 1 here, 1 here, 1 here, and 1 here. Meaning that we shall have the integral of 1 from 0 to 2 is equals to a times 1 plus b times 1 plus c times 1. And the integral from 0 to 2 of 1 dx is the same as x from 0 to 2. This is 2 minus 0, which is 2. So we get the equation a plus b plus c is 2. Next, we substitute f of x is equals to x. So if f of x is equals to x, then f of 0.5 will be 0.5, f of 1 will be 1, and f of 1.5 will be 1.5. So those are the values that we are going to substitute when we consider the case f of x is equals to x. So in this case, we have the integral from 0 to 2 x dx is equals to a times 0.5 plus b times 1 plus c times 1.5. And we end up with the equation 0.5a plus b plus 1.5c is equals to 2. Notice that the integral from 0 to 2 of x dx will give us a half x squared, and x increases from 0 to 2, which is a half into 4 minus 0. And this will give us 4 over 2, which is 2. So we have that equation. Now, when f of x is equals to x squared, the last value, if f of x is equals to x squared, then f of 0.5 will be 0.5 squared, which is 0.25. And similarly, f of 1 will be 1 squared. F of 1.5 will be 1.5 squared. Then we substitute and integrate. The integral of x squared will give us x cubed over 3. When we put x is 2, then we get 8 over 3. So we get the third equation. So we now have 3 equations in 3 unknowns. The first equation was a plus b plus c is equals to 2. The second equation is 0.5a plus b plus 1.5c is equals to 2. And the third equation is the one we have here. 0.25a plus b plus 2.25c is equals to 8 all over 3. Now, these are 3 equations in 3 unknowns. If you want to solve these ones, you can easily eliminate b from these equations. So you can take the first equation, subtract the second equation, that will eliminate the unknown b. Then you can take the first equation, subtract the third equation, again you eliminate b. So you are left with 2 equations in 2 unknowns. Then you can eliminate one of the unknowns. So once you do that, you get the value of a is 4 over 3, b is negative 2 over 3, and c is 4 over 3. Then you substitute back and you get the method. This now is a 3-point method. So you see that now using this method is easy. We just need to evaluate the value of the function at 0.5, at 1, and at 1.5. So we consider this integral, for example. The function here, f of x is equals to x minus 2 divided by x squared plus 3. So this is the function that we need to evaluate at these 3 points. At x is equals to 0.5, at x is equals to 1, and at x is 1.5. So we shall write the formula. See the coefficient 4 over 3 times this function evaluated at x is equals to 0.5 minus 2 over 3. The same function evaluated at x is 1, plus the third term we have the coefficient 4 over 3. Then the function is evaluated at x is 1.5. Once we do that, we get the value is negative 0.575 approximately. So in this case, we can develop a method, whether we want a 2-point, a 3-point, or a 4-point. We can easily develop a method to solve a particular integral. We can easily develop a method to solve a particular integral. There are other examples down here. I'll be giving you this note so that you go through the other examples given here.